I want to develop the equations of relative motion. First I'll do it in one dimension, and then I'll quickly extend that to 2 dimensions. But before I do that, I want to go over something about position vectors and derivatives of those to give us velocity vectors. Let's start with just a position x. This might be the position of some point P here in space relative to some coordinate axes here. This could be the x-axis and this could be the y-axis. And maybe this point P is moving in time. We would call x its position, and if that thing is moving in time, then its position will change, and we could talk about the velocity of that point as x2 minus x1 over delta t. And that would be its average velocity. Now the instantaneous velocity, we've talked about this before. We just put a v for it. It would be, this will be delta x over delta t, by the way. The instantaneous velocity would be the limit as delta t goes toward 0 of delta x over delta t. You shrink the time interval down for which you're considering the thing more and more, and in that limit, as that goes to 0, this ratio will equal the instantaneous velocity. And they go through this in the book showing how it's true for a graph of a curve. And that's the instantaneous velocity. Now we can do the same thing with a position vector. We can talk about a position vector r of a point in space that might be moving, and its velocity, average velocity of that point, would equal r2 minus r1 with arrows on top, divided by delta t. Its instantaneous velocity, again, is going to equal the limit as delta t goes to 0 of r2 minus r1 over delta t. And this is also written as dr dt, derivatives, something you're starting to learn about in calculus, and maybe you're at the point where you're actually performing derivatives. Now, these are vectors, but you take the derivative of one component at a time, and you're doing scalar equations. And so that is a velocity. If we wanted an acceleration, we would do the exact same thing with the velocity vectors that we do with the position vectors, and the acceleration will equal dv dt. Okay. So keep that in mind, keep these definitions of the derivative in mind, that we can just take the velocity is the derivative of the position with respect to time. Back to our 3 points that are on a line here. This is one-dimensional motion, and I'm going to draw some position vectors below them, but they would actually represent positions up on this line. So I'll start off with one that just goes from here to here and starts at A and ends at B. This is the position of B with respect to A. And I'm putting an arrow on top of it. We don't have to in one dimension. We're just fine using one-dimensional vectors, but that's okay. This will still work. And then I can also have a vector that points from here to here. That would go from B to C. This would be the position of C with respect to B. And then I can draw one that goes all the way from A to C. Do I have a dying pin? This would be the position of C with respect to A. And so these are 3 different position vectors here. But I think you can probably see that this vector plus this one equals this vector. And so we can say that the position of C with respect to A is equal to the position of B with respect to A plus the position of C with respect to B. And this relation is pretty much what all of these relative velocity formulas depend on. Now, these are just position vectors, but I can take time derivatives of this equation. I'd take the time derivative of the left side, and I would get the velocity of C with respect to A. If I take the derivative of the right side, I have the derivative of a sum, but the derivative of the sum is the sum of the derivatives. So the derivative of this, it's the velocity of B with respect to A. And this would be, when I take its time derivative, would be the velocity of C with respect to B. So just by looking at these position vectors and seeing how this one is the sum of these two, I can also get that this velocity, the velocity of C with respect to A, will equal the velocity of B with respect to A plus the velocity of C with respect to B. This is the form that you saw for two-dimensional relative motion, relative velocities, but it works for one-dimensional as well. We just happen to put arrows on them. Now, let me show you how this will look for 2 dimensions. It isn't a whole lot harder. I'm going to start off with just 3 points again, A, B, and C, but this time they're not along a line. This is 2-dimensional space here that we're talking about, and this would extend to 3-dimensional space as well, although we're not going to deal with that in this class. This is the position of B with respect to A, our B slash A. The vector here, this is the position of C with respect to B, so our C slash B. The vector sum of these two will point all the way from A to C. That's the way vectors add. And this also happens to be the position of C with respect to A. So in 3 dimensions, we have the position of C with respect to A is equal to the position of B with respect to A plus the position of C with respect to B. All right, that's just position vectors. Now, suppose A is fixed. This is a point attached to the Earth, and we think of the Earth as an unmoving thing in these problems. We're kind of going back to the times of Aristotle and pretending that. Now, here's some point in space. This could be someone walking along a street away from A at a constant speed, or any kind of speed for that matter. And C might be some bird that's flying up in the air relative to this, well, relative to everything. This is a bird flying up in the air maybe. So there's a velocity for B and there's a velocity for C. But because this expression is true, if we take time derivatives of these things, I'll end up with the velocity of C with respect to A. That could be the velocity of the bird flying with respect to that person standing there on the ground, will equal the velocity of B with respect to A. B is the person who's walking down the street, so this would be their velocity, plus the velocity of the bird with respect to B. So that's the velocity of C with respect to B. This person's walking down the street away from them. They'll have a velocity with respect to them. If they're watching this bird moving through the air at the same time, that bird will have a velocity with respect to them. And the sum of those two velocities will equal the velocity of this bird with respect to that point. This is the 2-dimensional relative motion equation. And we've been seeing some examples of that. We're going to see some more here. Now, there's one other thing that I wanted to show you. A couple days ago when we were studying rolling motion, I looked at determined the centripetal acceleration of a point on the tread of a tire out here on the edge of the tire as the tire is rolling along. Now I'm going to show you how that will be purely centripetal acceleration. And it seems baffling because I mentioned that the actual path of this thing moving along here looks like this. It touches the ground, it goes up in the air, and it just keeps doing this weird thing like this. Every time it touches, it does that. At its high point, it's actually the diameter of the tire above the ground down here. And it's doing this crazy thing, but let me show you what its acceleration is. First of all, we've got the center of the tire, or the center of the wheel, and this would be the position of the center of the tire with respect to the earth. And this could be any point on the earth, just happens to be there. Okay. Then, at some given instant, this is the point or the vector that points from the center of the tire to this piece of tread that we're studying, okay? Some particular point on the tire. And that's the position of the tread with respect to the center of the tire. And we'll also have the position of that piece of tread with respect to some fixed point on the earth. And something that we can write is that this vector is equal to this one plus this one. Oh, did I write? Oh, somewhere I did. I wrote it there. That refers to this one. Anyway, the position of the tread, piece of tread on the tire, a particular piece of tread with respect to the earth, will equal the position of the center of the tire with respect to the earth plus the position of that piece of tread with respect to the center of the tire. So those are our position vectors. Now, I can take a derivative of each one of these things, just like I did before, and I'll have that the velocity of that piece of tread with respect to the earth will equal the velocity of the center of the tire with respect to the earth plus the velocity of that piece of tread with respect to the center of the tire. Okay, let's talk about these things. The velocity of the center of the tire with respect to the earth. As the car drives down the road, the center of the tire, or the center of the wheel, goes in a straight line with constant speed. We're assuming the car is moving with constant speed. And this is the same as the velocity of the car which is constant. Okay, so that's part of it. Now, this is the motion of that piece of tread with respect to the center of the wheel. This is pure circular motion. Okay. It keeps changing direction constantly, but it's always tangential to the tire, but it's got a constant magnitude and just keeps doing its thing there. Okay, now the sum of those two is what gives rise to this crazy motion when we actually graph the position as a function of time. We add this constant vector to this crazy vector that's pointing in different directions all the time. and then analyze it at every given time, and we get strange motion. But let's take a derivative of this. Let's figure out the acceleration of that tire with respect to the earth. Okay, well, we take a time derivative of this. Well, we take the time derivative of this to get this. We take the time derivative of this, and it's a constant. Its time derivative is 0, because when you look at the limit as delta t goes towards 0 of delta v c/e over delta t, the numerator is always 0 because it's constant. So that's just 0. And so this one's gone. This is the only thing we have. And this is pure circular motion. It doesn't change in magnitude, but it does in direction. And that's what comes out to be the v squared over r. And it's constantly changing. But if I figure out the magnitude of it, that's what it will be, and that's the purely centripetal acceleration. And so even though it's doing this crazy motion, when you subtract out the constant velocity that the center of the wheel has, you get purely centripetal motion. And when you calculate the acceleration, that's the only acceleration that that piece of tread out there on the edge of the tire happens to have. And so it was okay that we calculated it and ignored the fact that the car was actually rolling along.